In the second part of this video on the Java Collection Framework, we will discuss two implementations of the list interface, which are the array list and the linked list. We will provide an example that illustrates using an array list to create a sorted list. In addition, we will explain how linked lists themselves are implemented using an example of a stack implemented directly with a singly linked list. We begin with a discussion of the list interface. A list is a collection that is stored in sequential or linear order. That means a list contains a first element, a second element, and so on. The list interface contains methods that are implemented in both the array list and linked list class. Let's consider some of the most frequently used methods in the list interface. The add method appends the element to the end of the list. Notice that the type E indicates that this interface is a generic one. Although the return type is Boolean, the return value has no significance because it always returns true. The next add method inserts the element at the position specified by the first parameter index. The remove method removes the element at position index and returns the element that it removes. The get method returns the element at position index without removing it. The index of method returns the first occurrence of the element passed to it as a parameter. It returns a -1 if that element is not in the list. Next, we consider the array list class. As we mentioned earlier, the array list class implements the list interface, which means that all the methods defined in the list interface are implemented by this class. Unlike an array, the size of an array list does not need to be specified when it is instantiated, and it can grow to accommodate however many elements are needed. Internally, array lists are represented with arrays. When an element is added that exceeds the amount of space currently allocated, a larger array is allocated and the old array is copied to the new one. The new array is twice the size of the original one, so this process does not need to be repeated too frequently. Next, we examine a program that uses an array list to implement a sorted list. The input to this program is a file of integers, which is opened in this statement. Next, the array list is instantiated. Notice that the type of the reference is the interface list, whereas the type of the object is array list. Declaring the reference as list ensures that this program only uses methods that are specified in that interface. Consequently, we could replace array list with linked list and this program would still compile and run correctly. It would not, however, be as efficient. This loop repeats as long as the file is not empty. On each iteration, another integer is read in from the input file. The inner while loop uses a fundamental technique for finding the location where the element must be inserted to ensure that the list remains sorted. It linearly searches the array until it finds an element that is greater than or equal to the element that is to be inserted. Notice the compound while condition. The order of the two relations is important because the first acts as a guard on the second. If the first is false, the AND operator short circuits, preventing the possibility of an array subscript out of bounds. Once the position is located, the add method is called to insert the integer in its proper location. The approach used here is similar to that used by the insertion sort algorithm. Scrolling down to the remaining lines of this method, we see that once all the values have been read in and inserted into the array list, the list is output. The values displayed will now be listed in ascending order. Next, let's run this program. Notice that the list of integers is indeed sorted. Next, we consider the other kind of list, a linked list. Linked lists contain one node for each data element. Each node contains a reference to the data. Unlike array lists, linked lists only use as much memory as needed. Linked lists require links for each node which add to memory usage. Singly linked lists usually contain a reference to the next node in the list. Doubly linked lists contain references to both the previous and next nodes. The Java linked list class is implemented with a doubly linked list. Adjacent nodes in a linked list are not necessarily in adjacent memory locations. Elements can be efficiently added to both ends of a linked list, whereas with an array list, adding to the end can be done efficiently, but adding to the front requires shifting all of the elements in the array. We have already seen uses of the Java linked list class, so our next example will demonstrate how a simple singly linked list is implemented. It will be a stack that implements stack interface. Because this class implements stack interface, one can replace array stack with link stack in any program where the type of the stack was defined to be stack interface. This nested class defines the type of one node of the singly linked list. It is a generic class like the outer class. Notice that it has been declared static because unlike nested classes that are used to implement event handlers, it does not require access to the instance variables of the outer class. In fact, in languages that have the syntax of records or structures, it could be declared in that fashion because it contains only instance variables but no methods. The first instance variable contains the actual data. The second one is a link that points to the previous node. Normally in a singly linked list, the link points to the next node. But when implementing a stack, it is more meaningful to regard that link as pointing to the previous node. The outer class contains one instance variable of type node. It is a reference to the node that is at the top of the stack. When the stack is empty, as it is initially, it contains a null reference. The push method accepts a parameter that contains the data element item. The first step is to create a new node. The data that was passed in as a parameter is then copied to the instance variable data of that node. The previous reference contained in top is copied to the instance variable previous of the node, so that it points to the node that was previously the top node. Then the node that was allocated in the first line becomes the new top node of the linked list. Let's scroll down to the two remaining methods. The first of those two is the pop method. It requires no parameters, but it does return the data in the node that will be popped. The first check is to ensure that an attempt is not being made to pop an empty stack. If it is, a null is returned. Otherwise, the data in the top node is copied to the local variable item. It is necessary to save this value because once the top node is popped, it will no longer be accessible. Then the instance variable top is changed to point to the node that was previously the top node. That action results in the top node of the list being removed. Because there are no longer any references to that node, it becomes garbage and will be automatically garbage collected. Finally, what was saved in the local variable item is returned. The isEmpty method returns whether top is null, which is true when the stack is empty. Next, we illustrate how a singly linked list is constructed when the push method is called. Initially, the reference top is null, which we illustrated by the diagonal line. The first step is to allocate a new node and save its reference in the local variable newTop. Next, the value in item that was passed in as a parameter is copied into the data member of the new node. So as not to overcomplicate the diagram, we have illustrated this step by placing the value 5 directly in the box that represents the data member. Keep in mind that this item is an object, so what is really copied in is a reference to the object that contains the value 5. Then the reference that is currently in top, which in this case is a null, is copied into the previous member of the new node. The final step is to copy the reference to the new node, which is in new top, into top. So now top points to the one node in this linked list. Now let's see what happens when push is called a second time. Another node is allocated and its reference is stored in new top. The value 2 in item is copied to the data member of the new node. The reference in top is copied to the previous member of the new node. So now the second node points to the first. Because it points to the previous node, we have named that member previous. Finally, the reference in new top is copied to top, so top now points to the second node, which is the last node allocated. Let's illustrate one more call to push. Again, a node is allocated and its reference is stored in new top. The value 7 in item is copied to the data member of the new node. The reference in top is copied to the previous member of the new node. So now the third node points to the second one. Finally, the reference in new top is copied to top. So top now points to the third node, which is the last node allocated. Next, we illustrate several calls to pop. First, the value 7 in the data member of the node pointed to by top is copied to the local variable item. It is necessary to save it because after the next step, this node will no longer be accessible. Top is changed to what is currently in top.previous. This change means that top will now point to the second node rather than the third. This is the step that actually pops the top node. Then the value that was saved in item is returned. At this point, the node that was popped becomes garbage because there are no longer any references to it. Automatic garbage collection returns it to the free pool of memory. Pop is now called a second time. The value 2 in the data member of the node pointed to by top is copied to the local variable. Top is changed to what is currently in top.previous. This change means that top will now point to the first node rather than the second. Then the value that was saved in item is returned. Again, automatic garbage collection collects the now inaccessible node. Finally, let's see what happens when pop is called a final time. The value 5 in the data member of the node pointed to by top is copied to the local variable item. Top is changed to what is currently in top.previous. This change means that top will now contain a null, which indicates that the stack is empty. The value that was saved in item is returned. Finally, automatic garbage collection collects the now inaccessible node.